So now we have Yagiz, who is a Node core computer, and from my favorite name title for a company, Noonlight. That sounds great. And Daniel. Daniel's a computer science professor at the Data Science Laboratory in the University of Quebec. And they're going to be talking about Ada parsing millions of URLs per second. So, on you go.
Hello. So, hi, I'm Yagiz. Today we're going to talk about parsing millions of URLs per second and our work that we did with Node.js and the URL parser implementation Ada.
Yeah, hello, I'm Daniel Lemire, and I'm a professor, and I do software performance.
Yeah.
So we're very focused in this work on performance, and sometimes people, when you're working on a node, you ask, well, why should I care with performance? And so to motivate the issue, we have a few arguments why you should care. Obviously, having a more performant system can reduce cost. Instead of using 12 nodes, you might use 6, which might be better. Even if you don't have this effect, even if you're using just one node, having more performance allows you to have more performant applications, so maybe your latency can go down. One thing that people forget is that if you have a system that's not very performant, what ends up happening is that you have to do all sorts of nasty tricks to make things faster, like having more parallelism and so forth, and these add complexity. So if you have a more performant-based system, you can avoid those. And of course, you prefer not to cause climate change through your software. So the core result of our work was much faster URL parsing in Node. So according to Raphael, who writes the state of the Node performance, we compare to Node 18, Node 20 as significantly faster URL parsing performance. The improvement is something of the order of 400%, which I think you would agree is quite significant.
So this is one of those codes from James, from the Node.js TSC member and a Cloudflare engineer. Just set a benchmark for a code change, go from 11 seconds to complete down to about half a second to complete. This makes me very happy. It's nice to see a happy engineer. Referencing adding Ada URL to Cloudflare workers, that indicates 22 times faster URL parsing for Cloudflare workers. Before we start about the implementations and our optimizations that we did on URL parsing, let's give some brief information about the structure of an URL. So this is an example of a URL that consists of protocol, username, and password, which are optional. We have a host name, we have an optional port, we have path name, search, and hash. And as you can see, there are some requirements, such as search starts with a question mark, hash starts with a hashtag, hash can be an empty string, search can be an empty string, and so on and so forth.
So you might think, well, this is fairly simple, and I can write a URL parser in in an evening. You're probably wrong. So basically, our our implementation is about 20,000 lines of C++ code. So to illustrate why this might be a problem, let's consider some examples. So first of all, maybe the URL is not made of ASCII characters, so you might have arbitrary Unicode inputs. You might have a file URL. File URLs are somewhat complicated. They require special handling. You might, of course, have arbitrary URLs, such as a JavaScript URL. You have to support percent encoding, decoding. You have fun effects with path names. For example, in the example there with the dots, this is actually equivalent to having, because you have a single dot and a double dots, this is equivalent to having /c as the path name, which is not entirely obvious. You also need to support things like IPv4, IPv6 addresses with all their possible variants. So it can get a little bit crazy, like it's in this example here on the slide, where it's maybe not a form you're supposed to know. In our work, we're supporting what is the latest and best standard, the one that Node supports. So it's what working group URL standard. It differs quite a bit from what other systems support. So if you take the input string that is above here with 711, so this is actually an actual URL that we found on the internet, so I took it as an actual example. So if you parse it with a PHP or Python using their runtime libraries, they're basically not doing any processing. They're just splitting the input strings, and they're not modifying anything. So they're not basically supporting any standard. They're just assuming that you did the parsing yourself somehow. The what working group URL normalized string looks as follows, as in this examples. So you have puny code, you need to do that, and then you need to handle the double dot, and then you need to convert Montreal to, well, this person encoded version. In curl, well, you use curl. Everyone should know curl. It's a standard tool, and they've got an API to do URL parsing. So they don't support what working group what working group URL standard. They support conventional RFCs, and as you can see, they don't do puny code encoding. The Go runtime does its own thing. I don't quite understand it. So it ends up like that. So it's neither curl nor what working group. That's the standard library, by the way.
So there are some assumptions with URL parsing. These are the two ones that I got triggered the most. That's why I wanted to include it. Does URL parsing really matter? Is it a bottleneck to some performance metric? To be honest, I care more about JS runtimes to have CI/CD processes faster and more parallelized. This is one of the assumptions. The other one is URLs are free. You don't gain anything by overloading them, and this talk is all about that. So before we start about what the impact is and what's the overhead is that, here's a small example benchmark that can run in any Node version. This is why we wanted to use this particular benchmark to show the indication about the cost and overhead of only parsing a URL. So this is a Fastify example. There's two different post endpoints. One of them is a simple one, which just gets the body, the JSON body, and just returns it without doing anything. The other one is a post body that parses it and then returns the href version of it, which is a string. And at the bottom, you will see what the example output is, which is like a really long string that contains most of those components in the URL. So in 18.15, the simple benchmark just didn't do anything, was running 60,000 requests per second. And just including a single new URL, it was going down by more than 10%. Which was around 50,000. So a single URL parser was causing 10% performance degradation on a simple HTTP request. So because of that, we wrote a library called Ada, called after my daughter, Ada Nizipli. It's a full what working group URL supported URL parser. There's no dependency, full portability. We don't have ICU. We implement everything from scratch in the most performant way possible. It's over 20,000 lines of code. It's a work of 25 different contributors, and it's available under Apache 2.0 and MIT dual licensed. It's available on ada.url/ada on GitHub. Yep.
So before we included it in Node, we benchmarked it against competitors written in C and Rust and C++. So the blue line there, as you can see on the left, is our speed, the speed of Ada in millions of URLs parsed per second. We are also comparing with, in orange, there's another C++ library that is similar to ours, but somewhat slower. We're also comparing against to boost a set of libraries, they have a URL parser. It does not support the WHAT working group standard. And then there's the Rust URL library, which does support the WHAT working group URL standard. And then there's curl. As you can see, curl is somewhat slower than the others. And we're significantly faster by a factor of 2 or 3. Importantly, we do support the WHAT working group URL standard is actually a living standard, so it evolves, it changes all the time. And we believe we're probably the most up-to-date implementation. We updated, according to my co-author, we are updated within 24 hours when it changes. And so as you can see, just right there by this evidence, we believe that we might be the fastest standard compliant library in the world. So we're not, there are too many lines of code, and it's C++. Not everyone wants to see C++ in the morning, but we'll still, but we'll still cover very briefly some of the tricks that we use. There's nothing magical, it's just hard work. So one of the tricks that we use is one of the problems that's interesting is that when you receive the protocol, so you figure out where the protocol is, it's easy to start off the string. You must identify whether it's a special protocol. So the special protocols are defined by the standard. There are HTTP, HTTPS, file, FTP, and so forth. And you must quickly recognize them. So you could the naive implementation would be just to take your string and compare it against 5 different strings. That's fast, but it's not as fast as it could be. So what we do as a trick is that we use the fact that if you have the length of the protocol and the first character, it's enough to distinguish. So that's what perfect hashing means. It's enough to distinguish uniquely a special protocol. So what you do is it's a mathematical formula. You take 2 times the length of the protocol times the value, the Unicode value of the first character, and then you basically take modulo 8, and it gives you a number between 0 and 7, which points into a table. And for example, if you have a string of 4 characters that starts with H, then you know if it's a special protocol, then it must be HTTP. So then at that point, you do one string comparison. If it's successful, then you know you have HTTP. And then you store an integer value for the rest of the processing. So you do very few arbitrary string comparison. Another very standard trick that we use, but we put to good use, is that instead, sometimes we have to characterize the character contents in some string. So what we do, instead of doing a bunch of arithmetic, is that we use a table. So we create a 256-byte table, and then in the table it tells you basically whether you've got bad character or good character, and you just look up each character in the table. Now that's character by character processing. It's not super fast, but most processors can do 2 loads per cycle. So basically, you can achieve something close to 1 character process per cycle. Sometimes that's without doing anything fancier. That's probably the best you can expect. Now, don't worry about this slide. You don't need to understand everything here. But the idea is that sometimes you want to do better than that. You want to be able to process 16 characters at a time, for example. That's much better. Now, all of your laptops here are either 64-bit ARM-based, in which case they support Neon instruction for 16-byte with 16-byte registers. Otherwise, you have x64 processors, which support at least SSE2, which again have 16-byte registers. And so basically what you do is you load the data 16-byte by 16-byte, and then you do comparisons in parallel. So using, basically it's called SIMD, so you do data parallel comparison. And that's much faster in practice, in our experience. Of course, the compiler can do that automatically for you. It's called auto-vectorization, but compilers are not always able to do it for all sorts of reasons. So we found that it was very beneficial to do it by hand. Future version might support fancier instruction sets, but these are the basic ones, SSE2 and Neon.
So on top of those C++ optimizations, we optimize specifically for runtimes that have the cost of crossing the boundary of JavaScript and C++. For the use case of Node.js, crossing the C++ and JavaScript land means that there is a serialization cost of huge strings. And because of that, in the initial version of Ada, we had all of those components like protocol, username, host, port, and we were returning different strings on top of href to the user land, and we were constructing the URL class and returning those properties. But this had a really huge cost, because if you have a really large string, the length of the string determines the serialization cost, and it's huge. So in order to reduce it, we introduced, with the Ada 2.0, we introduced a single string that is only constructed while you are parsing that string. So there's no string allocations. Unnecessary string allocations are done. And we are storing the offsets of each of those components. So protocol and username and host start, host end, port that you see at the bottom of the screen. Those protocols, those offsets are constructed and sent to the JavaScript land, and the URL class right now that's used in Node.js slices the href in order to return those properties, which provide a really significant performance boost with the latest changes. Here's a small JavaScript benchmark. So for any input, we are iterating through all of those lines in our data set. We are constructing the length, and we are parsing the URL. We are returning the href and the size of it. This is mostly because we don't want V8 to optimize and trick our benchmark that it's performing faster than it is. That's why we are always appending and summing up to the length property. This benchmark is available on Ada URL, JS URL, benchmark URL at the bottom of the screen. Please take a look at it. It's important to share benchmarks. And for the sake of this benchmark, here are our results. On Node 18.15.0, we were parsing around 0.8 million URLs per second. At that time, at that same exact version, Deno was parsing around 0.9 million URLs, and Bun was parsing 1.5 million URLs per second. With Node 2.1.0, which includes Ada 2.0, we are right now parsing almost 2.9 or 2.8 million URLs per second, which is roughly 2 times faster than Bun and 3 times faster than Deno right now.
So, so we have, as you demonstrated, we have extensive benchmarks with lots of data, and everything is online. The Ada library is, we consider it safe and efficient. So it's all coded using modern C++ techniques. Things like string views, for example, that were introduced formally in C++ 17. Modern C++ is quite different from old school C++, and there's lots of benefits. We're using the best available tools. So, for example, we're using sanitizers that automatically detect buffer overruns and problem memory. We're doing a lot of work with fuzzing. So basically, we're throwing random inputs into the library and trying to make it crash, trying very hard. And we have an extensive framework of unit tests with thousands and thousands of tests for covering the entire scope of this specification. And basically, in practice, and this is public, you can go see, we've encountered very, very few bugs. Mostly the bugs were related to standard. They were all fixed within a few hours. They're very easy. So if you find a bug in the library, because of how it's built, it's very easy for us. We don't need to do crazy things like go into a debugger and scan the code. It's pretty much straightforward if there's a bug to identify where it is, and we can fix it very quickly.
So Ada is right now available in the language of your choice. It's included in Node 18, 19, and 20 of Node.js. On top of that, we have C bindings that you can literally use it anywhere in the world, anywhere in any programming languages.
Anywhere in the world, too.
Yeah. So we have Rust bindings, Go bindings, Python, and R, and each of those implementations are almost as it's one of those fastest URL parsers in their particular implementations, in their particular languages. So often, yeah, and as far as we know, Ada is the only WHATGL URL parser that supports a wide range of programming languages that's available through all languages. So you can you can go to adaurl.com, which includes a playground that's accessible through WebAssembly, so you can play around and pass a string that runs the actual parser instead of the browser's new URL. You can take a look at my blog, yagiz.co, and you can take a look at Daniel's blog, lemire.me. And if you have any questions, we'll be more than happy to answer them.
Oh, amazing. Thank you ever so much. That was brilliant. Now, we do have a bit of time for some questions. So does anybody have a question? Oh, you've given them too much info. Oh, here we go. Let me get the mic to you. No, just you.
Hey, hi, good morning. Oh my God, this is kind of a trippy talk to like walk into on day 2 because it's like every slide is like, what? Amazing. So a few questions. One is, so I, back in the day, used to contribute to WPT, which is like the web platform tests, which is the conformance suite for browsers and the web. And so I'm curious, there are definitely tests that Mozilla and all the browsers are running to test their implementation of the WHATGL standard. And so I'm curious, did you use any of those tests? Did you convert any of those tests to run in a Node context? I'm curious, like, and then if so, could you share the results of that? And then, yeah.
Yeah, I can answer to that. So we have our own WPT runner that tracks that repository and keeps our own tests up to date with less than 24 hours uptime. We run every test in the web platform test repository in regards of URL parsing. WPT has around 83% of test coverage, so it doesn't cover anything. And on top of that, we have the double that amount of size for the tests. And we also contributed to WPT, opened multiple issues, and helped other implementers to find bugs in their own URL parsing, such as Boost, curl, and even WebKit.
Okay, so if I'm hearing you correctly, you're saying that yes, 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 and you also helped fix the health of the entire internet in the process, right?
Yes.
Just confirm. Okay. Yeah. Okay.
That's
so
one way.
Again, like, fantastic morning talk. The other question I had was, I'm curious. Amazing how fast it is, but have you actually, just for shits and giggles, like used ChatGPT to say, okay, make this go faster, figure out how to make this go faster?
No, we did not.
I kind of did particular benchmarks, but the recommendations are not that it doesn't work. It's not sufficient for our case because this is an extremely specified and extremely unique application that general performance optimizations does not apply to, because URL parsing is so huge. It contains more than one, maybe more than 10 different performance issues that we have to encounter, and each one of them is unique to each other.
But if I may, very quickly, so if you, for example, you've seen the crazy C++ code, if you ask ChatGPT, if you tell it, can I locate such and such characters using, ARM, Neon, blah, 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 blah. It will actually generate something that looks like this code, but if you don't understand it, it doesn't help you very much because then you have to still fix it and integrate it into your code. But
well, it's probably using your code to generate that code. So.
Yeah, it's probably circular too.
Yeah.
Okay, last question since nobody has one. So the other, like, so you have awesome fuzzy testing, right? To kind of see how to break it. I'm curious if you would consider using ChatGPT to generate more fuzzy data, for those tests.
So
especially on the security side.
We are using Google OSS Fuzz, which has around 70% test coverage right now, just for fuzzing, and it's pretty good. We didn't try ChatGPT, but yeah, that works as well.
Cool, awesome. Just curious. Thanks.
Thank you very much. Anyone else got any questions?
There's
one over here. Getting my steps in.
Thanks. As a room of people that maybe write URLs, are there features we should be using or not using in order to optimize performance from a usage standpoint? So maybe we should be staying away from puny code encoded things if we can help it, or things like that. Are there any of those features which are particularly painful on the processing?
Yeah, so everything that has to do with Unicode processing is kind of slow because of how it's designed. But that's actually part of, there's as much we can do still. And actually, some of these cases we'd like to optimize further. We did not discuss the detail of the benchmarks, but we use collections of different collections of realistic URLs that are found in practice. But you can certainly find counterexamples using, for example, international characters, which would slow things down considerably. But we're probably going to, the goal is that you should not have to change your URLs for performance. The system should be fast. And in some cases, it could be faster, yes. We're going to even improve that.
Awesome, thanks.
Well, thank you very much. Could you please give it up one more time for Daniel and Yagiz?